Так, ну что, I think we can start. Паша, там YouTube идет нормально?
Ну, я сейчас зайду, ну, Zoom вроде говорит, что нормально.
Хорошо. Okay, so, Kostya, go ahead.
Okay, so yeah, thank you for inviting me to the seminar. It's really nice to present this work here. So let me start by writing the title. So Liouville quantum gravity. And integrable systems. So so in this talk, I want to guess in the first part I'll talk about the Liouville, and then I'll talk how it relates to the more common stuff to the audience. So let me start by some kind of introduction in Liouville gravity. So and let me start from the idea. So Liouville quantum gravity is a two-dimensional quantum gravity. Well, and so what's the idea? The idea is that when we speak, let's say when in physics we speak about gravity, it's generally a theory of a metric. Theory of metrics. Well, so it's a 2D quantum gravity. It's theory of metrics on Riemann surfaces. And well, what is quantum? Quantum means that we sum over all possible configurations. Sum over all possible configurations. And so how it is usually done in physics? Usually it is done using the idea of the path integral. And yeah, let me briefly describe how it works in this case. So let's say we have a Riemann surface, sigma, with a metric G. So here G is not a genus, but rather a metric. So Riemannian metric on sigma. And let's say some matter data. So let's say we're considering theory of gravity, but not just pure gravity, but with some matter. So this is matter. Some additional data on the surface. So the most common I would say example is where, okay, maybe I'll write it like this. So where F, let's say, is a map from our Riemann surface to some Riemannian, usually a Kähler manifold. So manifold. Or, so what will be the case in this talk is a choice of a line of like root of a line of a canonical bundle of a surface. So F is a line bundle such that, let's say, L power Q is isomorphic to canonical bundle of a surface. Okay, and so how do we build a gravity with this data? So build a partition function. So partition function, which is given by a functional integral. So over all possible metrics G, let's say sum over topologies of surface, which is, well, it's not very complicated to do. Sum over topologies. And then we take all the path integral in our matter, which is denoted by the letter F, and then we weight it with the usual weighting quantum field theory. So it's, let's say, -1/h of the action of the theory, and the action will be S matter.
Excuse me. Could you please switch to the full screen mode? Because otherwise I see only just like 3 lines. In the right upper right corner of your sheet.
I guess here? No.
Lower. Here.
Okay. Great, thank you.
Much better.
So, okay, so the action of the matter depends on our matter and on the metric, because it should be a covariant action, and then there should be action of gravity, which depends on G. And idea of Polyakov in 81, I guess, is that, well, what can we do? We can split the integral in metrics, in, well, in the conformal class and the conformal factor. So this is representative. And we know that conformal classes are the same as complex structures. Represent for image surface representatives of class in the moduli space. Let's say some model of curves. Complex curves, and this guy is a conformal prefactor. And the integral splits into some finite dimensional integral and infinite dimensional integral. So we have integral over, let's say, moduli space, say of genus G, for example. We can take the lemma for compactification of the moduli space, but it's some details. Some measure on this moduli space, maybe I'll call it G and use straight G because it's a finite dimensional measure, which is well defined. And then we still have infinite dimensional stuff, which is, well, there is this conformal prefactor. So we integrate over possible conformal prefactors, and then we integrate over all possible matter fields. And the result is that, so in this case we still get action of matter. It doesn't change. And then the gravity turns out to be some theory of this one field phi on our image surface, and it's called the Liouville action of phi. Well, and times some Jacobian, some coordinate transformation times Jacobian, which one can write using Faddeev-Popov-Gauss, for example. And what is the Liouville action? So S Liouville phi is the integral over our image surface of like a volume form on it. Let's say we put coordinates with holomorphic coordinate psi. So square root of G times times the standard kinetic term for one complex valued field, plus the Liouville theorem, which is non-trivial. You write the dependence on psi here. Okay, plus some other non-relevant terms which make all the thing covariant. Where so B is a constant. Well, usually it's in R, but for generality I'll write it. So it's a complex number that is determined by the matter. Okay. So why this code is a Liouville theory? Because, well, so equations of motion of this action, so other Lagrange equations of this action, equations have the following form: is del bar of phi is equal to I think 2b mu exponent of 2b phi, which is, so this guy is just a classical equation, classical Liouville equations. And so what are the solutions of this equation? If we solve this equation and interpret phi as a conformal factor of the metric G hat, then the solutions are going to be a surface of constant negative curvature. So this is the name. And well, so this is the approach which how the Liouville theory originally was found, but it's not very convenient to work with it. Oh yeah, by the way, I forgot to ask, what is the length of the talk?
Okay, usually it's okay between hour and a half and 2 hours.
I see. Okay, great. So right. So it's not usually very convenient to work with Liouville theory like using path integral, and there are different formalisms. So now there are different formalisms to work with it. And let me. Yeah. So the classical formalism is a formalism of CFT. So formalism of conformal field series. Well, by Zamolodchikov brothers. And many other people. And recently, which is really nice, there have been another mathematical approach, which is approach from the point of view of probability theory approach. Where, well, so look at this path integral, and actually it can be defined. So at least path integral in the metric can be defined in terms of so-called Gaussian free field in probability theory. Maybe I'll cite a paper here. By Kupianin, Rod, and Vargas, 19th, where the authors managed to reproduce. So it's a very recent paper, and the authors managed to reproduce what I will define later, the 3-point function, a correlation function for the Liouville theory using this approach, which is really nice. Anyway, so I will use the CFT approach, CFT formalism.
Kostya, may I ask you a question?
Sure.
At what moment your problem became elliptic, so you get not D'Alembert but rather Laplace operator? You made a
yeah. So
big turn.
Yeah, in the beginning.
Signature of G.
Yeah, in the beginning. So we work with Euclidean signatures to get rid of all the complications of analysis and this kind of stuff. So we start with Euclidean signature. So the usual understanding of well, so how to work with Lorentzian signatures is, well, so we compute our theory in Euclidean signatures, and then we try to do some analytic continuation for correlation functions, which is like some Wick rotation or something. So this is Liouville theory is almost always considered Euclidean.
Kostya, and in this when you say about this probability theory, I just never heard of this. What is the system where they exactly? You say that they compute these 3-point functions.
Yeah.
And what is the ensemble? Just
the starting point. So yeah, I'm not sure about the details, but it's so it's called a Gaussian free field. So it's basically so what is a Gaussian free field? It's so consider an eigenbasis of Laplace operator into D, and then so the coefficients in front of eigenvectors of Laplace operator, those are just random variables, Gaussian random variables. So this is the theory, the field, like, or the free field they construct, and then they compute the measure, which is basically the Liouville action. But instead of quantum field, they use this Gaussian free field, and then they take expectation value. And
I'm just afraid of the word free.
Right. So the point is, yeah, the point is that indeed, in order to build the theory, they use exactly what I said. So it's like all the coefficients in this expansion are Gaussian random variables. And the interesting thing is that the whole Liouville non-trivial things, they come from the action. So they compute expectation values of something like this. Yes. Yeah, I don't know if it answers the question, but that's
Okay. No, but okay.
mhm. Yeah, other questions so far? Okay, great. So yeah, I'll work with a more classical approach of CFT. Yeah, and I think that these guys and some other people, like in particular in Columbia Math Department, are working on proving conformal bootstrap and like drawing other interesting like CFT things from the approach, and so far it works, which is according to me is very remarkable, because it's in a certain sense it's a direct realization of path integral and then derivation of CFT formalisms starting from path integral, which is I think anyway. So CFT. So as I guess most people here know, conformal field theories are defined by two pieces of data, determined by two pieces of data. Let's say we work with Virasoro algebra conformal field theories. Those are spectrum, state space, and 3-point functions, structure constants. And then the conformal bootstrap allows to reconstruct all the interesting quantities in CFT using these two pieces of data. So what are these for Liouville? So spectrum for Liouville. So it's a slightly delicate question, in the sense that usually in CFTs people are familiar with, like, for example, WZW CFTs, which lead to equations like Knižnik's homological equation or minimal models, which lead to BPZ equation. For all these models, the spectrum is discrete, and it's some finite sum of representations of some algebras. The for Liouville theory, it's not the case. So the spectrum is continuous. It's integral of the following representations of Gaussian algebra. So I'll explain the notations a bit later. Times phi. So where? So the thing is, in brackets is the notation, and phi. Well, phi the same field as here, so it's Liouville's field, which lets you think that in path integral formalisms, those states would correspond to vertex operators of this form, and Q is just B plus B inverse. It's called a Liouville background charge. So it's a constant. So P is a parameter. We integrate over all real P. And so this thing here is actually a Fermat model of the Virasoro algebra of Virasoro, where the central charge is given by usual formula. So 1 plus 6q squared, or 1 plus 6 b inverse plus b squared. And highest weight or conformal dimension, highest weight, let's call it delta Liouville P, which is so q squared over 4 plus p squared. And well, yeah, so the spectrum consists of this continuous number of Fermat models.
So, excuse me, I'd like to understand the notation better.
Sure.
Why do we write phi in the square bracket if the square bracket denotes just Fermat module, which is given by two numbers?
Right.
Right.
So the point is that in two-dimensional CFTs, there is what's called operator state correspondence, meaning that every state in the Hilbert space in the spectrum is corresponds to some vertex operator, and highest weights. So highest weights of this model, they correspond to vertex operator precisely of this form. So it's exponent of the Liouville field. Of this,
Okay. Then another question. This obviously takes into account only say holomorphic part of Liouville, right?
Yeah, exactly.
Yeah,
that's a good question. So actually is, yeah, that's a good remark. So actually, how do I write it? Yeah, maybe. Sorry, 1 second. Yeah, that's a good remark. Oh man, hope it works. Yes, it didn't cut the whole thing. Okay, so it's the same thing, the anti-holomorphic part of the same thing. Yeah, exactly. So it's a theory of spin zero, meaning that the anti-holomorphic part is precisely the same as the holomorphic part.
So all the states have symmetric highest weight.
Yeah.
Thank you.
May I ask a question? Do you say
so
that
if the states have not?
Do you say that fields with p and with minus p are different?
Well, yeah, that's so usually people write like this, but there is an identification of the spectrum exactly, which is Z2 identification, which so Z2 identification.
You can write integral over p from 0 to infinity.
Yeah, I didn't specify the contour precisely for that reason, but exactly. Which is not trivial, yeah, but can be derived.
Thank you.
Other questions? So this is a spectrum, and now speak about 3-point functions. Three-point functions. And 3-point functions are given by well-known formula. So say, okay, maybe write it like this. Sorry. Okay. So we take 3 vertex operators. 1, 5, 0, let's say. A2, 5, 1. A3, 5, infinity. So here, yeah, here you see I'm writing these vertex operators, which corresponds to, well, to highest weights. So AI is a half of this exponent over here. So this is given by a DOZZ formula. And yeah, door not as logical as logic. If I don't see much reason in writing it down here, because if you know it, you know it, and if you don't know it, then I better say that it's a meromorphic function in A1, A2, A3, and B. Some explicitly given function. Yeah. So first thing we can notice is that actually, so it's a meromorphic function in A1, A2, A3. In particular, we can analytically continue it from values of A in the spectrum. It makes perfect sense. But yeah, so we can actually take relation functions of field which do not belong to the spectrum, a field of this form. And this leads to some subtleties, but I don't want to talk about it too much, even though they're important in gravity. So yeah, so maybe I mentioned them a bit. Yeah, another thing.
Kostya, sorry, but I probably had asked before, but when you say spectrum, what is the precise definition of spectrum?
Well, so spectrum is a how do I say it? Is a set of fields which appears in the operator product expansion. So when we take Liouville,
you mean in the intermediate channels?
Exactly. Yeah. Exactly.
Only those fields, but when you consider 3-point functions, then their charges, these A's can be arbitrary, right?
Exactly. Yeah. So the point is that I guess the theory like if you want your theory to really behave in the best possible way, then you're restricted to considering correlation functions from the spectrum. But in Liouville theory, it turns out that you can actually consider correlation functions whose charges are analytically continued to arbitrary complex numbers. But so the intermediate fields will always be in the spectrum, and so you might get poles at certain values of A1, A2, A3. Yeah.
I think maybe a more intuitive definition will be from the sense of radial quantization that dilatation operator acts as Hamiltonian, and the spectrum in terms of this Hamiltonian are dimensions of primary.
Yeah, but the point is that you consider primary fields with any arbitrary value of A, and well they might have even complex conformal dimensions, conformal complex eigenvalues of the Hamiltonian, but so the physical meaning of this I don't want to discuss this too much, but you can do this.
Can we say a priori something about the positions of the poles?
Yeah. A priori, no, I don't think so. It's yeah.
Does not follow from some principles at all.
No. 3-point functions never follow. Like in principle, 3-point functions are not determined by CFT itself. They're determined by the concrete CFT, so by the specified given CFT. So they
okay, thank you. Thanks.
And actually, they have quite a varied structure. So yeah, if I have time, I can comment on this later.
Okay.
So some poles are at points where you expect them to be, like based on some considerations, but some poles are, right.
So basically, you mean now this old logic of Polyakov that when you integrate over Liouville zero mode, you can expect some poles at the positions being proportional to this I don't know Katz values, yeah. But
Yeah.
if you try to construct a function with the poles and residues given by free fields, then you get some extra poles you don't see a priori. Yeah, that's what you say.
Yeah,
that
yeah.
the half of
Yeah,
them should be
I'd
same.
rather say the phenomenon which I encountered is you encounter no poles where you'd like them to be. Depending, it's actually based on some duality with minimal models, which I might comment on later. So right. So this formula, yeah, it was discovered in the 90s, but more recent. So more recent attention due to AGT, where this comes from localization in 4D gauge theories, some regularization of infinite products. Yeah, and I was told, so this story I don't know, but last time I gave this talk, I was told that actually you can also understand them. So these 3-point functions from the point of view of you know, through some huge algebra, which contains Virasora, but this I don't know, so I won't talk about this anymore. Okay, this is so far what I wanted to say about the Liouville field theory. And the matter content for today is consists of Virasora minimal models, I guess R. Virasora minimal models. Yeah, I guess most of people here know it, but I say a couple of words anyway. So the spectrum, again, so this is a CFT. Those are CFTs. Oh man. Wait, what? Yeah, sorry, just a second. Something not very nice happened. Okay, great. I managed to. So it apparently I cannot erase things to the left of my screen, but anyway. So right. So for a coprime number, for a coprime pair of numbers q and p, let's say p is greater than q, we have a Virasora minimal model. Let's say, let me call it m q over p. So with the central charge less than 1, smaller than 1, so 1 minus 6 b inverse minus b, where b is square root of q over p. So, and yeah, I use the notation from the Liouville, well, because it will be the connection with gravity, but it's the same b. And spectrum, discrete spectrum. So it's a sum, or m n. And again, I'm using the same notation. So this is big phi. It doesn't have to do with the Liouville phi. And those denote so vertex operators. Inside. And these guys are Virasora irreps. So Virasora irreducible representations. where sum is mn in the cuts table, so-called cuts table.
Excuse me again for annoying questions.
Sure.
No,
again,
here we have tensor product, right?
Yeah, sure. Times anti-holomorphic.
Don't write it, just to check that I understand correctly.
Yeah. Yeah, so those are also spin zero. So we have symmetric. So yeah, the holomorphic and anti-holomorphic conformal dimensions. So the fields are the same. So what is a cuts table? So it's a table of size q minus 1 times p minus 1, and then mn just run through integer points inside this rectangle. So those Virasoro irreps are factors of highest weight representations. So in this case, Verma models, Virasoro highest weight representations are not irreducible. They contain Verma submodels, and the contribution to the spectrum is the factor of the Verma model with respect to all the submodels. So there are actually infinite number of submodels, and so conform of vertex operators of conformal dimension of highest weight, conformal dimension, you just call it delta mn and don't write the explicit formula, which is again quadratic in B and B inverse. Okay, and so 3-point functions.
Sorry again, and in the previous case of the Liouville spectrum, all the Verma modules were irreducible?
Yeah, so the point is that in the Liouville case, all the Verma models from the spectrum are irreducible. That's true.
Okay, thanks.
So if you
sorry, indeed you had a real B in that case.
Sorry, in the Liouville,
Yes.
you can have, in fact, I think you can have arbitrary complex B maybe beside from the some half line in the complex plane. I think from a negative like yeah, sorry, it's so your central charge actually has to be greater than 1, I believe. Like your central charge could be arbitrary complex number, which is not real smaller than 1. So if you're in this case, then you can define Liouville. If your central charge is like real number smaller than 1, then you cannot. So the DOZZ formula has a singularity there. Yeah, but in my talk, B will be well, Q over P.
Kostya, I have a maybe stupid question.
Sure.
You stated from the beginning that the Liouville theory is given by the partition function involving some path integral. Then you start stating it as a theory with certain states plus 3-point correlation function. Is there a way to derive these properties from the first principle, from the partition function, or it's just a kind of answer, just guess?
Yeah, so this is actually a good point. So the point is that originally I think it was maybe people will correct me. I think it was by Disler Kavai, maybe some other people. It was kind of a guess that a CFT, like a Liouville field theory as defined by partition function can be reduced to some conformal field theory. So there was some assumption of the measure, there was some computations, but it was very imprecise. I'm not sure if it was later clarified in physical literature, but what I know is that so in this probability theory approach, so people start with probability probability realization of the path integral, and then they can prove in certain cases they can prove the conformal field theory approach. They can prove the bootstrap approach. So which is So in this sense, it can be derived mathematically at least up to a
But
certain point.
at this moment, we are talking just about possible version of this theory with no direct proof from the path integral, correct?
Yeah, but the point is that probabilistic definition is basically some realization of path integral. So it's
Okay, you see, in Euclidean situation, the path integral can be made rigorous. So
exactly.
they are doing a work that should be done by physicists earlier, probably.
Yeah. So I know this physical. So this physical proof by I think Disser and Kavai. But yeah, I didn't read through it carefully, but I believe that there are like some strong assumptions. But like under those assumptions, you can actually prove something.
Thank you.
From a physical point of view. But yeah, maybe there are more recent considerations. It's just that I don't know. Right. So 3-point functions in the Liouville theory. Let me write them like this. Okay, they are well known. They were first computed by Datsenko and Fatiev in the 80s. And then I'll write them in the following form. So Datsenko and Fatiev. I don't remember the exact year. 87 maybe. So I'll write them as some fusion rules, constant. Times the DOZZ formula, which is some analytic expression. Let me just write it like this. Some analytic expression. And then I write this as so it's 1 or 0. It's 1 if fusion rules are satisfied. So if in this case something like M3 is in M1 minus M2 plus 1, and M1 minus M2 plus 3 dots, M1 plus M2 minus 1. Same for ends. And so, yeah, I don't want to write this in details, but same for same. If we flip, Mn to Q minus M, B minus N. So yeah, I forgot to tell that there is a Z2 symmetry in the CAS table, which identifies fields. So Z2 symmetry around the central point, which identifies fields which have the same conformal dimension. So and 0 otherwise. So apart from this Z2 technicality, these fusion rules precisely work like 2 copies of fusion rules for representations of SL2. So if you interpret like M1, M2, M3 as SL2 spins, and N1, N2, and 3 as spins of another SL2, copy of SL2, then these fusion rules are the same as fusion rules for this representation. So if let's say representation of spin M3 appears in representation of spin M1, M2, and the same for ends. Okay, those are the correlation three-point functions. And so we all know that in CFTs, the correlation functions are analytic functions. Let's say, don't know, phi 1 and 1 of xi1 up to phi mk and k xik are analytic in real analytic functions in zeta1 up to zeta k, which are so sesquilinear, so Hermitian combinations. Maybe I should write it from big H, I don't know. Combinations of Virasoro conformal blocks, which are some representation theoretic objects which can be computed. And many people from the audience know about them better than me. So, and structure constants of three-point functions. Great. Yeah, which that have a that transform as sections of bundles over in this case, so if it's in genus G, on sigma of genus G, sections of bundles, or in this case mg k, maybe bar, under the coordinate transformations or on the Riemann surface, and do zeta1 zeta k. And
Okay.
so this,
Sorry, I have two questions.
Mhm.
First of all, you have two kinds of fields, Liouville field and meta field.
yeah,
You mentioned correlation function for Liouville theory and for minimal models.
yeah.
Is there interaction, are there correlation functions between involving minimal models, fields, and
Yeah, so
Liouville field? This is
Right.
the first question.
So the answer is actually in this case no, and this is what I'm going to talk about actually, like right after this. So how do they interact? Yeah. But the short answer is no, there is no correlation.
So the interaction is of different nature. I don't understand what it means. If there are no,
Yeah, let me. Yeah, maybe because
okay.
I'm.
And the other question. So if this xi, you treat them as a point of the Riemann surface.
Yeah.
But then you summarize. You take sum over all Riemann surfaces. What that means?
Yeah.
So
what
is actually the correlation function? Where are positions of your fields?
Yeah. So this is precisely. I mean, I would ask, I think, both of your questions, right? Like in 2 minutes. Because so far I described you two conformal field theories, which are so far both of them are not Liouville gravity. So one of them is Liouville conformal field theory, another is minimal models. So to make a Liouville gravity out of them, I'll need to do something which I'm going to do right now. So and this will both include answering to the questions where we insert our vertex separators and how they related. So is it fine with you if I answer it just like a couple of minutes?
On my question.
Yeah, if you feel unsatisfied, please feel free to ask them again after I write this. Is it fine?
Go ahead.
Yeah. Other questions so far? Right. So yeah, one thing which I would notice is that in the case, in the Liouville case, these bundles are actually infinite dimensional. These bundles are infinite dimensional. But it's not very nice. They're not very nice. It's just that there is some transformation law involving these correlation functions. Okay. Now, yeah, now precisely to answer these questions is that I finished with just conformal field theories, and I want to. So let us build the Liouville gravity out of them, out of two CFTs above. Sorry. Yeah, I guess my pen doesn't write on the bottom of the screen. On the right hand side of the screen, rather. Two CFTs above. So the observables of okay, how do I put it? Just 1 second. Okay, for every minimal model primary field, which is a vertex space corresponding to the highest weight of the Riemann model, phi mn, we define a gravity observable, so a Liouville gravity observable, which I will call bold O, with the same indices, which is usually called the dressed or gravitationally dressed field phi mn. So, and the correlation numbers of the Liouville gravity are defined as follows. Rather, of these observables of Liouville gravity. So OM1 and 1 up to, and they don't have insertion positions. Don't have insertion positions. O, M, K, and K, let's say in genus G, are defined as integrals over moduli space of curves, genus G curves with K punctures. Well, of products of two conformal blocks. So we take conformal block, which is built out of this the fields phi mn corresponding to our observables bold OMN, and so that at some points psi1, phi mk, nk, psi k. So multiply it by another conformal block. Sorry, by another correlation function. Those are correlation functions. 2a1 phi psi1. So it's a correlation function in minimal models. And up to exponent of 2ak phi of psi k. It's a correlation function in Liouville. Times some holomorphic function, maybe, which comes from Fadeev-Popov ghosts. It's some explicitly defined holomorphic function, so it's not too complicated. So then defined. Let's for simplicity.
It is holomorphic or meromorphic or what? Where is if it's holomorphic on what? On MGK?
Yeah, let me let me just make it a bit more precise. What do I want to say? Let me just.
Is it something like imaginary part of tau?
No, it's a conformal block of the Fourier. Maybe I just write it more precisely so that so this is genus 0, for example, and then I can write it explicitly. So it's present, like, it's present only in the case where of the sphere and torus, where we need to fix some continuous symmetries of the corresponding surface. So, for example, for the sphere, we multiply it by some correlation number, say C of zeta1, C of zeta2, C of zeta3. So this is holomorphic function is correlation function of Ghosts. Function of Ghosts.
Excuse me, C is a holomorphic function of psi1 position.
So this is a vertex operator of the Ghost theory. So vertex operator of Faddeev-Popov Ghosts.
You mean that otherwise we would have written integral over m0 k-3, right? And fix positions of 3 points.
Yeah, but the point of that's basically what we're doing. But
this is a more symmetric way to write the same thing, right?
Well, it is. So this m0k, it's some symmetric power of a sphere, like k. It's, I guess, p1 power k-3 up to some rational equivalence. So this function is so this correlation function is basically explicit. It's something like.
I'm afraid that after putting bar, it's much more complicated than you just wrote.
Sorry.
When you put
yeah. So I don't want to.
But the integral doesn't depend on whether you put a bar or not.
Yeah. So
it is only only explains that the integrand can be extended to the compactified space.
Yeah, that's right.
It describes the properties of the integrand.
That's right.
Not the integral itself.
So right, in this case, so in the case of a sphere, this function is something. So this Ghost correlation function looks something like this. So it's just a product of zeta I minus zeta j for like zeta1, zeta3, zeta3, zeta2, zeta3 in some powers, which I think are something like 2, but yeah, I'm not completely sure. So it's some very explicit function which is not very interesting. That's the whole point. Yeah, and this is integrated over all the remaining assertions.
But sorry, what's the measure? Is this a
So let me finish the integral. So d zeta. So for the sphere, it's completely explicit formula. So which I'm writing zeta I squared. Okay. So let's discuss this formula a bit. Let's stop for a moment. Okay. So it's a gravity correlation number in the case of a sphere, where so we pick any coordinate chart on our moduli space, which in this case can be just we fix 3 positions and we vary all other positions of the insertions. And this will be open coordinate chart in this moduli space. And in this open coordinate chart, we can compute this function as an analytic function of zetas. We can compute this function as an analytic function of zetas. So this is an analytic function of zetas, and this is explicit. So this is a measure. This is just in this case it is just this. So why this is true? So how does this work? Well, I told you earlier that well, you know, you know, I guess that correlation functions have some transformation laws with respect to coordinate transformations of. So on 0, 0 is just coordinate transformations of this space are just coordinate transformations of these zetas, and so this prefactor, so the integrand transforms as well as a as a volume form on M0K. So in particular, if we remove this integration factor, then this product of correlation functions transforms as a density on M0K. So now, what are phis? So phis are, you know, we know, so phis are defined by this M and N's. What are A1 up to AK? So those are charges of the corresponding Liouville vertex operators, Liouville primaries, which are completely determined. So the numbers A1 up to AK are determined by this requirement uniquely. I mean, up to Liouville reflection, determined by this requirement. So there is a simple formula. So those are related with so-called KPZ exponents. Maybe I'll write related because they're not exactly. So once again, let's think about gravity. Let's consider just minimal model theory with primaries phi, like, you know, phi mn, and then I want to build some gravity correlation function out of these phis. Well, if we take the ordinary correlation function, of course it depends. Let's say on a sphere for simplicity, so we don't take into account the moduli of the Riemann surface. So first of all, what I want to do in gravity, I want to get rid of the positions of insertion because those are you know, geometry dependent, and we integrate our all possible geometries. We cannot do this. We cannot do this as it is because this correlation function doesn't transform as a density on the moduli space. So we cannot integrate it coordinate independently integrated over the moduli space. So what is the solution? The solution is to change the transformation law. How we can do it? Well, we have gravity primary fields which have their own conformal transformations. So we dress our middle model fields with the appropriate gravity field, so that the conformal transformation of this whole factor. So the Gauss are just to fix the usual procedure to fix the continuous symmetries of the spheres. And what do I want to say? Right. Yeah. And so this is how we can both get rid of the coordinate dependence, and this is the way the matter fields interact with the gravity. So where I should also say, and for the Liouville theory, so B, which was a parameter which entered like everything, it's a parameter which determines the central charge of Liouville theory, is equal to Q over P from middle model. So this is a very non-trivial fact that, in fact, I think it was argued by Polyakov in the original paper that actually in the case where I'm considering like theory of gravity with matter, if your matter is a conformal field theories, or maybe it was done in Disserkova. I'm not sure about this where the statement was done, but in the case where your matter is conformal, then the whole interaction between your matter and gravity is through the fact that central charge is determined by the matter content, and that the gravitational dressing, so the Liouville correlations are determined by the metric correlation. But other than that, they don't interact. So this is a beautiful fact about two-dimensional conformal gravity.
Excuse me, when you wrote initially, when you wrote this formula, you mentioned that the integrand is a conformal block, or it is a correlation function.
It's a correlation function.
So no summation over blocks, just everything is inside brackets, right?
Yeah. So this is already a correlation function. It's
Okay.
not a holomorphic function. It's a real analytic function. Already a correlation function. Okay, so yeah, Igor, does this answer your questions?
Thank you.
Right. So yeah. So this is how people build a Liouville gravity. How people define it. So maybe examples. The problem with these numbers is you see that you can define them. I mean, there is a question about convergence, but they usually do. The main problem is that how to compute them. The definition itself is, it looks like what we do in topological gravity. It's integral of some differential forms in moduli space of curves. But whereas in moduli space of curves, usually you consider in topological gravity, usually consider some cohomology classes which have some natural like intersection theory meaning. So and you can compute the integrals, by many different ways. And here you have some complicated product of conformal of bunch of conformal blocks, correlation, structure constants, and how to work this expression is unclear. So this is a complete mess. But there are some examples. So 3 points.
So I'm sorry, but in general case, if we restrict to the 3-point case, what will happen?
Yeah. So that's that's exactly what I'm going to do. So example 3-point correlation number. So OM1 and 1 point on a sphere. So today I'll only discuss correlation numbers on spheres and disks, so in genus 0, in open and closed versions. I hope I'll have some time for open version. So N2, N2, and M3, N3. Well, as we all know that moduli space of 3 punctured curves is just a single point, so there is no integration at all. And the correlation function, sorry, this structure, this correlation function is just structure constants. So all the coordinate dependence is killed by this Ghost factor. So this is why it's, you can see why it's needed, what it does in the case of 3 points. So this is just a product of the minimal model, structure constant, M1 and 1, M2 and 2, M3 and 3, and the Liouville structure constant for A1, A2, A3, DOZ formula. And the beautiful fact that it's essentially doesn't depend on M and N's other than the fusion rules, through the fusion rule. So this is, remember the fusion rule constant, which is 0, 1, M1 and 1, M2 and 2, M3 and 3, times some constant. So this constant doesn't depend on anything. It doesn't depend on M's, on N's. Well, it depends on the choice of the minimal model. It's just not interesting. And the rest is just the normalization for the fields. So they're usually called lag factors. So lag of AI. 3-point functions are very, very simple. So those are just normalizations. It's basically fusion rules for minimal model. Okay.
How are they computed? Again, I'm just missing a point. You need to do something to get the answer.
Yeah. So
answer with any indication how one can do it.
Yeah, sure. So how do we do this? Let's take this definition. First of all, k equal to 3. So there is no integration over here. It's just product of 3 correlation functions for 3 series. We take any 3 points we like. So what is this 3-point function? let's say 0, 1, infinity. Doesn't matter. So the 3-point correlation function for the minimal model is given by the Senko-Fatiev formulas. So it's the structure constant times the the fusion rule constant times the 3-point function for Liouville for minimal model, which is explicit function. So we write down this function. Then we compute the Liouville correlation function. So the Liouville correlation function is given by the Diozzi formula. So we know A1, A2, and A3 because, as I told, there is a simple formula which relates AI with the corresponding MI and I. So that in a unique way. Then we write down this analytic formula, Diozzi formula, and then we just multiply these two things. So here there is also the fusion rule structure constant. I didn't write it down. And then we compute it. So and most of the things cancel. Most of the things cancel. And the remaining things have this form. So maybe a remarkable fact is that these two structure. So why one way to think why this cancellation happens is that these two structure constants are solutions to the same difference set of difference equation with some different parameter. It's again it's some fact which follows from computations of these two structure constants. So example 2, 4-point functions. Yeah, maybe I return to the full screen. 4-point correlation numbers. Well, in this case, this is just integral over M04, which is a sphere. Oh, M04 bar is sphere with sorry, M04 is sphere with 3 punctures, but M04 bar is just a sphere. And there are four fields here. So the integral has the following form. So if we fix, let's say, 3 points against 0, 1, infinity, get something like this. Again, 4-point conformal block, 4-point correlation function rather for minimal model. Again, same insertion points. So the Gauss correlation function in this coordinates, I think, looks like this. And then, yeah, it's just D to Z. So we know how to compute 4-point conformal blocks, at least as a power series. So this integral we can do so, and this is isomorphic to just sphere CP1 with coordinate Z. So in one way to do this, we can do this numerically. And we did this. But so there is a way by Belavin and Zamolodchikov from 2004. So there is a clever way to reduce most of the numbers. Let's say not most, but a large portion of the 4-point numbers to 3-point numbers. using the so-called higher equations of motion in the Liouville theory. Higher equations motion in Liouville. Sorry. Yes. And yeah, let me say in the words that. So what does this mean? So first of all, for any minimal model, they have some subset of 4-point correlation numbers where they can apply some recursion which reduces this to 3-point numbers. So this kind of looks like what happens in topological theories, where you can compute, for example, 4-point functions, degenerating your curve into your sphere with 4 points with 2 sphere with 3 points, intersecting with 1 point. Yeah, here the situation looks a bit more complicated. So this 4-point function is a sum of 3 contributions corresponding to each one of 3 possible degenerations of your curve, and there is some background contributions. So there are 4 contributions in total to these 4-point correlation numbers, and this in particular, well, so from this point, it seems like it is not a topological field theory in the sense of axioms of topological field theories, because the recursion is different. Right. And like much later, Volodya, Belavin, and I think it was 16. So we computed all 4-point numbers in the case M2 over P. So where Q is equal to, where Q is one of these 2 numbers defining the minimal model. So it's a height of the cut table.
Question: what are these numbers? So
Okay.
4-point correlation. So what are these numbers you are mentioning?
Yeah. So yeah, I can write down explicit formula, which is not very enlightening. But what I plan to do.
I'm not asking about the explicit formula. I'm just saying where they are.
So what I want to relate them with, we want to relate them with 4-point numbers in a count of Q spin curves. So this is what I'm going to talk now.
But before, please. So you have 4-point correlation function. It's a function of harmonic cross ratio. Yeah.
So we take 4-point correlation functions.
What are numbers you are talking about?
Yes, we take so these functions are functions of harmonic of cross ratio of Z, and then the number is integral over Z of this product of correlation functions.
So you are talking about a function of Z depending. Oh, you integrate over Z.
So we integrate over the harmonic ratio, yeah.
And then so numbers is
so it doesn't depend
depending
on Z.
On A1, A4.
So A1. So numbers depend only on M1 and 1 up to M4 and 4. So A1 up to A4 are determined by M's.
So numbers, you mean this dependence on
so on M's.
Okay, thank you.
So yeah, so maybe I should say it again. So given a minimal model, any minimal model, we can define correlation numbers, so which are indexed by just primary fields of minimal models, and that's the only information they are indexed with. So we just take k primary fields from minimal models. We don't specify insertions, we don't specify any other information. And for each of these tuple, we have a number which is defined like this by this integral. But number is defined only by choice of minimal model and choice of k primaries in the minimal model. So it doesn't depend on anything else. Because all of this data is determined from A1 and some from this M's and N's. Because this is, all the positions of correlation functions are integrated, all the A's in Liouville correlation functions are defined by m's. Yeah, so there is no any other information. So what I want to do, I want to write a generating series.
Excuse me, could you repeat just again, what
Yeah.
does it mean m and then in brackets 2 over p? What?
Yeah, so minimal models were defined by a pair of coprime numbers, q and p, where q is height of the Katz table. And then, so we did it for q equal to 2 for Katz table of height.
I see.
So it's called the Lee-Yang series of the minimal models and of the minimal gravity correspondingly. Okay, and so 5 point, 6 point, etc. There is no no data at all. Higher genera. There is some data, something for torus 1 point blocks. Sorry, for torus 1 point numbers. I think by
and I guess 0 point also.
Yeah. And that's it. So there is also information about disk 1 point numbers. It's basically by Fatiev, Zamolodchikov, and then by Zamolodchikov and Zamolodchikov in like 0, 1, I think, and 0 something, and that's it. There is some idea how to compute all the numbers for a sphere, for example, using some recursion, but this is something like in particular I am working on slowly, but yeah, so far it's not done. But anyway, so this is this situation about these numbers. Yeah, and these formulas, so these formulas we got, like using some analytic considerations, we can check them numerically for four-point functions, which is great. So they agree with the definitions. And yeah, so the thing I want to get out of this discussion is so the Liouville generating series, Liouville partition function. So I denote this as f with indices L for Liouville, q over p, sorry, which stands for the minimal model we're talking about, q over p, g of 0. So the generating series will depend on variables lambda mn. So those are variables, formal variables, if you like, where mn again belong to the Katz table. So it is just a generating series of correlation functions on a sphere. So we take exponent of all the fields OMN, gravity fields, yeah, weighted by the lambda m's. So this is a formal power series. Formal power series in p minus 1, q minus 1 over 2 variables. So, and I want to compare it with some quantities from topological gravity. Okay. So, so this is what I wanted to tell about like Liouville, let's say on a sphere. So now I'm going to present the comparison result, or conjecture rather, and some results. So we take, as I already taught, we take the topological gravity as intersection theory of q-spin curves. Namely, so we take so for number q, which will be the same as q here, and well, so this topological gravity has state space V, which is spanned by, say, phi 1 up to phi q minus 1. This will also call identity on the state space. And it's endowed with a metric, eta, let's say eta AB, which is eta of phi I, phi A, phi B, is just delta A plus B, comma Q. And then the correlation numbers in this theory are defined as correlation numbers in Q-spin theory are defined as, so the notation is as follows. I guess it's more or less a standard notation. T tau D1 phi A1 up to tau dk phi AK. So this is a notation for D1th gravitational descendant of the field phi A1. So they defined as integrals or of some cohomology classes over a moduli space of curves. Let's say GK, sorry, MGK bar of some class which is called the Witten class. I think, yeah. So it's some cohomology class which is defined, by some push forward from some cohomology class on moduli space of curves with this qth root, choice of qth root of canonical bundle, and then as usual multiplied by the psi classes. So psi 1 power d1 wedge, it's wedge, psi k power dk. Psi classes are of course Chern classes of cotangent bundle at first marked point in this case.
Stupid question. Why the number of fields is just q minus 1? You should expect them to be p minus 1, q minus 1. Am I missing something?
So in Liouville gravity we have, yeah, exactly. So this is actually a good point. So in Liouville gravity we have two numbers, p and q, and the number of fields is p minus 1 times q minus 1 over 2.
No.
So here, so far we have.
I think that pq you have for matter field, not for Liouville.
Yeah, they're for matter field, but they are like in Liouville gravity.
Okay.
Yeah. So the point is that so far there is only q, and I'll explain shortly how p enters the.
These q are not primary fields. Or
Sorry?
there's some this phi1, phi q minus 1. Why
Yeah,
is
yeah.
so few primary fields here?
Yeah,
Variables.
they are. But they're not conformal fields. It's not a conformal field theory. So it is just it's just an enumerative theory. So this class is built as Euler class of some bundle over space of curves with so
this q has nothing to do with the previous p and q. Am I correct?
It will be like in a short while.
But at the moment it's just completely different.
Yeah. So far it's just a natural number. Yeah. So far q is a natural number, and this has nothing to do with conformal field theory. So this is just topological field theory, which is defined as follows. So there is a state space, there is a metric, and there is a bunch of correlation numbers which are indexed by this A's and this D's, which are defined just by integrals, well-known integrals over a moduli space of curves. So far it has nothing to do at all with the previous discussion. So now I'm describing.
Sorry. Should I think that the space of states is some phi times some tau to some power?
Yeah, I think like the whole state space will be like this.
Mm-hmm.
Yeah, but I think in terminology of cohomological field theory, of topological field theories, it's the descendants are usually not included.
Ah, okay.
It's some different terminology. Sorry, it's because so far, maybe I'll write more bars. So far it's completely different discussion. So I'm describing a theory which is well known and which we are going to compare to Liouville theory.
Sorry, is it correct that if p equals to 2, then we have two times more fields on the topological side than on the CFT side?
Sorry?
Initially, we had q minus 1 over 2 fields, and this q had to be odd.
So initially we had, in Liouville gravity, we had q minus 1 times p minus 1 over 2 fields. Here we have q minus 1 times infinity fields, because di's can run through any numbers.
I see.
Because for any, let me just like write a generating function. I hope it will be more clear. So those are some numbers which are well defined for any a1 up to ak inside 1q minus 1, and any d1 to dk greater or equal than 0. So they can run all the way through infinity. So far there are way more variables than Liouville. So we can define the generating function of genus 0 invariance numbers. So let me call this f 1 over q. So this is not f power 1 over q. Its superscript stands for q-spin curves, the classical notation. And then it will depend on infinite number of variables. So it's a formal power series, a and d. Sorry. So where a runs from 1 to q minus 1, and d runs from 1 to infinity. So it's infinity times q minus 1 times infinity variables.
It's q reduction of kp.
Exactly. So this, so let me just use the sentence. So this is logarithm of tau function of the dispersionless q's reduction of kp, exactly, or q's Gelfand hierarchy. So this is the whole point. So this is a usual generating function. K, A, and D. These correlation numbers. D1 phi A1 up to dk maybe 1 over k factorial phi ak times t. Maybe I put upper indices. Just more convenient here. A1 d1 t ak dk, common dk. This is product of variables. Okay, so this is generating series. And so what do I want to achieve? Oh yeah, sorry. And yeah, as Sigrid properly said, that this is log of tau q's Gelfand hierarchy, dispersionless of t. So it's a tau function, topological, okay, sorry. Tau function of the topological solution to the Qth dispersionless Gelfandiki or Qth reduction of Kp. So, and what do we want to do? We would like to compare this. We have to generate in series. So on the one hand side, we have the Liouville function, which depends, partition function, which depends on, first of all, it has two discrete labels, Q and P, prime labels. And then it depends on, so Q minus 1, P minus 1 over 2 variables in the cuts table. You want to compare it with the topological gravity partition function in genus 0 of T alpha D. So Q minus 1 times infinity variables. And there are two immediate problems. So the first problem in this comparison is that, well, so this function is labeled by two numbers. This is by one, so it doesn't depend on P. And second problem is that, well, we have different number of variables and we don't know how to identify them even if we do, even if we had same number. So let me explain you how we can solve these problems, both of them. So first, maybe like this. Sorry. Comparison. The first problem is, where is P in the right hand side? So the answer is that we have actually, we have to kind of forfeit our interpretation of integral over a moduli space of curves, and this is kind of clear because Liouville doesn't seem like a topological field theory. So, but what turns out to be actually important is that we have to take a different tau function, so different tau function of the Gelfandiki hierarchy. So we replace F1Q, the topological tau function, with log tau of a different solution to Kp, oh sorry, to Qth Gelfandiki. Well, it's also log tau of certain solution to Kp, but to Qth reduction of Kp. So, and how do we choose this? So this will depend on P, and how do we choose the solution?
So you need to replace truncated version of Virasoro constraint by something else, or you just
it still will be
initial
constraint.
data. You should choose a different initial data.
So I should choose a different dilaton shift. So I should deform my Virasoro a bit. So well, so this one satisfies
Virasoro or the initial data, because the tau of the solution is defined by initial data in X, say in
let me write it down. So satisfies Virasoro constraints. In particular, well, this satisfies only L-1 and L0, which completely determine this function in with initial data. So satisfies Virasoro constraints. In particular, the string equation. It actually satisfies W constraints, but it doesn't really matter. The L.
Yes, Kostya, I'm a bit confused. When you say for, you just consider the simplest case of P or Q equal to 2 or arbitrary?
Q is arbitrary. So then it will satisfy W constraints.
Then Virasoro constraints is not enough. Yeah, there are double constraints.
So for W constraints exactly. But for genus 0, the Virasoro constraint turned out to be enough, I believe. So, but I might be wrong. I think I'm true. So for genus 0.
It sounds strange, but I don't really know, because why for genus 0 these negative W's are inessential.
So the point is that basically, so how do you know this? I can reconstruct a solution to the hierarchy from solution to the string equation, and you know, there is a theorem that actually the solution to like certain form of the string equation satisfies.
I may guess what's going on. The usual string equation corresponds to okay, you have to, there are two operators, L and A, whose commutator is 1. So now he's going to choose one is of the order Q, the other of the order P. Am I right? So this is change of the somehow critical point.
Yeah, exactly. Change of a critical point. Yeah.
Okay.
So right. So satisfy the string equation where, in this case, the string equation looks like this. D twiddle alpha d, d over dt alpha d minus 1 plus eta alpha beta t alpha 0 t beta 0.
But from what I know, if you go to P or Q, both bigger than 1, then these T variables becomes not single valued. There would be some branches.
That's right. Yeah.
Am I right? Okay.
Yeah, it corresponds to different choices of solution of string equation. Yeah. T twiddle 1 1 is so this satisfies string equation with a dilaton shift, and others alpha d equal just t alpha d otherwise. Yeah, and the pith critical, what's called pith critical point in theory of matrix models, or yeah, different solution corresponds to. So we have to take a different dilaton shift. Different shift. So we define L minus 1 exponent of f1 over q comma p of the same set of variables, genus 0, by the string equation, where now we take okay, so we divide p by q with the remainder. So let's say p is equal to s times q plus p0, which is smaller than q. And then the dilaton shift for a PQ minimal model is replaced with the following one. So it's P0, S plus 1 has to be shifted by 1. And all other times have to be unshifted. So we take yeah, and as Igor said, that in the variable, like the function becomes the variables T alpha k become multivalued, which correspond to the fact that there will be some discrete three-dimensional solutions of string equation. And then we'll have to have a proper solution. And L minus 1 in this case, in genus 0, actually determines the tau function, again up to this choice of branch, this discrete choice. so which determines a Gelfand-Dickey solution. So yeah, it's somehow like we're taking a little continuation of the topological solution to get this, taking a different solution of Gelfand-Dickey to take the solution, and now we're somehow in a better shape. So we want to compare these two quantities. F1 over Q comma P, 0 of T's, T alpha D. Well, still there is a problem of identification of variables because this still depends on Q minus 1 times infinity variables. This still depends on Q minus 1 times P minus 1 variables over Q over 2 variables. And so the way to identify the variables is the following. So use the scaling C star action, if you like, on the both sides. And second of all is well, some additional fusion rule considerations. Let me explain myself. So yeah, maybe the most like kind of one of the most important things which was noticed like again back in KPZ, that in Liouville theory, so we have this parameter mu, which is called the cosmological constant in the Liouville theory because it's a coupling constant of the surface area in the action. So so all the correlation numbers of Liouville, they're not actually numbers. They depend on mu, which was this parameter. Sorry. And it enters the DOZZ formula, for example. Yeah, sorry, where is it? Yeah, here. Called cosmological constant. But the dependence is very trivial. Dependence is scaling dependence. So OM1 and 1 up to MK and K is equal to mu power Q minus sum over AI over 2B times the same correlation number evaluated at mu equal to 1. So this essentially this gives us scaling to the generating function. This gives the following scaling. So we replace mu with C times mu, and simultaneously replace all the times with P plus Q minus absolute value of M Q minus NP over 2Q. So this is a KPZ exponent, which appeared earlier. So this is up to some number, actually a value of AI. So A corresponds to this field anyway. Times lambda n. So there is some scaling. Scaling property on the left-hand side, and also for this critical point. So for this choice of dilaton shift, there is a scaling on the right-hand side. There is a scaling. Not all solution of Gelfand-Dickey have a scaling, but this one do have. And yeah, I think this is basically how this was identified originally. So originally was identified through the matrix models, but in matrix models, in the limit they become integrable models, and matrix models have scalings, and then scalings in matrix models were identified with scalings in Liouville theory. So also there is a scaling in the right hand side. And the scaling is, so when we do the following transformation, T alpha D goes to C power P plus Q plus alpha plus, sorry, what I'm talking about? Yeah, alpha plus D times Q over 2Q. So this actually, these formulas, they look nicer, not in the frame of variables of Geff and Dickey, but they became more nice in the frame of KP variables, because this alpha plus D times Q is basically the index of the corresponding KP variable. Anyway, for people who know this story. So in particular, T alpha P0, so the remainder of division of P over Q, comma S minus 1, scales as mu. Scales as the cosmological constant in the Liouville. Okay. So what's the idea of the identification? Now we can identify these two things not just as some just random power series in lots of variables, but we can identify them as power series with cis direction. And this is much more. So this becomes a finite dimensional problem. So first of all, we know that this has q minus 1 times p minus 1 over 2 variables, and we know their scalings. So we can leave in the Gelfand-Dickey partition function. We can leave only the variables which scale like lambda m. So we define. So sorry, we identify. So far, still naively. Let's say T alpha K, sorry, mu lambda mn with T alpha of mn and D of mn that scales the same under star with this star, and so those are natural scalings on both sides. So naively we can identify them and throw away all other variables. Throw away all other variables. So of course, for every pair mn, you have a unique t, unique Gelfand-Dickey time, which scales the same way. So throw away all other variables, so that we get q minus 1 times p minus 1 over 2 variables on the right hand side. Okay, and we're almost there. So the point is that the naive identification of variables, so we take lambda mn identified with t with the same scaling, doesn't work because just the numbers are different. And in principle, there is it's not natural to expect that naive identification would work because the observables in the Liouville theories are some conformal fields. There are observables in the topological gravity. Well, it's not even topological gravity anymore, right? But observables in topological gravity are some cohomology classes of completely different nature. So it's very strange to expect that they would have one-to-one correspondence. So actually, So there are this scaling invariant, C star invariant coordinate transformations. So T alpha D is equal to, say, I'll write them in general form, M N M1 plus sum over A M1 M2 N1 M2 N2 lambda M1 N1 times lambda M2 N2 plus etc. So polynomial, which is important because of the scaling condition. So the polynomial coordinate transformations. Oh, sorry. Can you hear me? Hello, can you hear me?
Yes.
Can you hear me? Oh, okay, great. Sorry, my something happened with my internet apparently. Oh, sorry. Okay, so right, coordinate transformations that are called the resonance transformations. So that after these transformations, after these coordinate transformations, so conjecture, the left-hand side is equal to the right-hand side. So where is it? Yeah, this formula. So after resonance transformations. Okay, and let me tell what is the result of this conjecture. So first of all, we don't know much about numbers in Liouville theory, so we can check this conjecture only as far only until our knowledge of Liouville finishes. But there are lots of results. So results. So it's Belavin and Zamolodchikov. 0.8, I guess. Oh, sorry. 0.8. Then there is Dubrovin, Belavin, Muhamedjanov. From 13. Then there is Volodya Belavin from 14. Then both of Belavins from 15, I guess. And then there is a paper by me and Volodya Belavin from 16. So we establish that for all known correlation numbers in Liouville, meaning for most numbers up to 4 points on a sphere, the resonance transformations, so this coordinate change, are uniquely determined by the fusion rules, by the minimal model fusion rules. And the conjecture holds. So the correlation numbers coincide after this coordinate change. The conjecture holds, well, up to some details. There are some weird phenomena which are still not completely understood. So let me summarize what I've said so far. Yeah, maybe I'll return to the fusion rules quickly. So the gravity 3-point correlation number, like it's some simple expression, but proportional to this factor, which is completely representation theoretical. So this is called a fusion rule for 3-point numbers. There are fusion rules for higher point numbers. So those are determined by minimal models. And in particular, well, if we want this conjecture to hold, then at least we need the correlation numbers on the right-hand side. So from Gelfand-Dickey tau function. After these resonance transformations, we want them to satisfy fusion rules of the minimal model. And this turns out to be a very strong restriction. So up to 4-point sphere, you know, all these people, including me, were able to determine these fusion rules through this requirement. So those are polynomials. You just write a general polynomial, and then you, general C-star invariant polynomial, and then you fix the constant using the requirement that fusion rules satisfied. So yeah, and so these people managed to compute these resonance transformations in a way that, yeah, for all, or I would say for almost all non-correlation numbers, after this transformation, the left, like the Liouville numbers coincide with this derivatives of this tau function, of this logarithm of tau function. So this is kind of the main conjecture and the main result of the story. I think I'm over time, but let me just finish with a couple of words about you know, what's also known in the directions. So first of all, this is Geno zero story. What about different topologies? So for higher Genera, there is a problem with Liouville. I didn't think too much about it, and I think people didn't do much computations again for torus for 1-point functions maybe. And so what I did instead, I did some computations in the case of disks. So there is a story for Liouville on the surfaces with boundary. It's called the boundary Liouville theory. And so, for example, 1-point correlation numbers were computed like in the beginning of 2000s by Fatiev, Zamolodchikov, and Zamolodchikov. And then there is enumerative theory of surfaces with boundary from the point of view of topological gravity. And this was done like originally by Pandaripanda, Solmer, Tesla, I guess. And then it was done by many other people for the case of spin curves, for example. And then the open invariants were defined. And then the Witten conjecture generalized also to the open case. So this open, you know, this generating function of invariance of the discounting on the right-hand side is also can be expressed through some quantities in Gelfand-Dickey integrable system, which is basically one disk 1-point correlation functions which we want to compare. They are like some sums of sphere 2-point functions. So those are sums of second derivatives of this function with some coefficients. And so yeah, in recently, a couple of years ago, me, Chai Harim, and Volodya Belavin managed to prove that using the same resonance transformations from the sphere, the Liouville gravity on the disk coincides with the up to 1-point function. Well, coincides with the disk 1-point function topological gravity. Okay, and yeah, so yeah, the main idea is to try to well, we want to make this statement in full generality for any topology. Yeah, the main idea is to try to find some structure in the Liouville theory, some recursion relations, some kind of analogs of string equation, Virasoro constraints, like, you know, given task structure or whatever structure we can do. But so far it's a work in progress. That's it. Thank you for listening.
Thank you. Are there questions?
Many, but not now.
No, I have a very general question. So on the right-hand side, when you take into account all genera, you should expect that you will recover the solution of not dispersionless, but
Exactly, yeah.
what would be what is the counterpart on the left-hand side?
Yeah, so the whole problem is that it can be defined, but so far it cannot be, so we don't know anything about it. So the conjecture that basically this statement holds in the full generality. So it holds in all genera, it holds in surfaces with boundaries, like, you know, for everything you can do in topological gravity or in integrable arcs. So the conjecture is that you can do this in Liouville theory.
Does that means that after proper change of variables, the partition function of the Liouville gravity, full Liouville gravity, is a solution of infinite.
Yeah, exactly. So this is the hope. This is the hope. The problem is that this coordinate change resonance transformations, they're not known in general. They are hard to compute. And so, for example, what we can try to do, we can take some string equation for the right-hand side, and then try to pull it back to the Liouville side using these resonance transformations, right? So we can just write the string equation in the coordinates lambda, and then we expect this to hold in the Liouville theory. I mean, not expect, but it should hold in the Liouville theory. But the problem is that the coordinate change is very complicated, and the string equation after the coordinate transformations becomes a complete mess. So it's not it's not obvious at the moment how the structures look after.
It is polynomial in lambdas, but of what degree?
So degree is well, it depends. So it's can be very high. It depends. It depends on the minimal model. So for any minimal model, there is a finite number of fields, and then the degree of this polynomial is identified is basically what. So why this is a polynomial? Why this is a finite degree? Because this should be C star invariant, and then like the just the condition that the scaling of the left hand side. So we cannot have, like, if we have very high degree in the right hand side, then the scaling will be like there is no variable on the left hand side to survive the scaling. So those are some degrees, yeah. There are formulas, but yeah, I don't so far I don't. There actually for 2, p series, for this Li-Yang series of minimal models, where this, the cut table is just one-dimensional basically. Its height is 1. There is a conjecture in this paper of 2008. There is a conjecture on the general form, because in KDV case, it's kind of like lots of things simplify. And there is a conjecture on the general form of these resonance informations, but it uses some orthogonal polynomials. So yeah, and this is one of the direction of the work, is that we're trying to understand, like, because if there is some simple structure behind these resonance transformations, then it will be, the hope is that we can easily find the structure of of integrable hierarchies of tau functions on the Liouville side, but so far it's not the case.
Thank you.
Also, yeah, also in the Liouville you can try to, so it's some kind of accounting theory. Well, it's much more complicated than usual cohomological theories, but we can try to do things like to try to do some geometric arguments, to try to derive string equation, like Dilaton equation, whatever. So how do you usually derive string equation? You plug like a identity field in your correlation function, and then you get string equation which is powerful enough to reconstruct the genus zero theory in the topological gravity case. But in Liouville, what happens if you plug the identity operator, you actually get a Dilaton equation, like analog of Dilaton equation. You just get the scaling. So in Liouville theory, there is a so there are some ideas how to find this recursion, but it's kind of complicated. So far it's not had been done. Only for 4-point functions they've been reduced to 3-point functions. But there are some ideas. So I think it's plausible that we can find the recursion for all correlation numbers, to reduce them to 1-point numbers.
Thank you.
May I ask you about
Sure.
probably the Liouville theory alone?
Sure.
Why do we consider only the vertex operators of the shape of exponential of phi, but not with pre-exponential?
So
Are
yeah,
they
that's a
all
good question.
descendants? What?
So that's a good question. So how to start to answer this question? So one thing I didn't tell you about is that the fields I'm considering, so the dressed minimal model fields, are not the only observables in the Liouville gravity. So physically, you can try to formally apply BRST quantization to the theory, and then your spectrum will be some space of cohomology of BRST operator, which is like explicit, like conformal theoretic operator, and then you can try to find all the states. And there are a lot, in fact. So there is, as far as I understand, I'm not sure, but I think that the expectation is there is a natural number times what I presented you, observables, but they're not really studied. So there is one set of observables which is studied, which are one I presented to you. There is another set which is actually used in this recursion relation, which I mentioned earlier, which are called ground ring states. And so yeah, so first, the first part of answer to a question is that actually there are more states in the gravity than I just presented. And also the logarithmic field, which is just the exponent, is also used in this construction. So this is also like it is used. But the problem with this field is that so it's a logarithmic field because exponent of your field of your Liouville field is a scaling factor of the metric, and so the pre-exponent is its logarithm. So it has some singular behavior. So yeah, it's what's called the logarithmic field, and it's kind of like it's not exactly, but it's kind of like a free boson. So in free boson theory, you usually consider only, vertex operator correspond only either to derivatives of your boson or to exponents of your boson. So in Liouville field, since the charge is twisted, the central charge is twisted, the derivatives actually don't work like in minimal models. In minimal models, you can realize them using this Coulomb-Gas representation or like screening operators rather. And the vertex operators all will be exponents of kind of your like twisted free field. Kind of same happens in Liouville.
Yeah, I see it's complicated.
Yeah, it's there is some more story to this actually, but so yeah. So
Thank
the
you.
point is that these guys are the easiest operators and the most natural operators, like the states which we can consider.
Mhm, mhm.
This is a short answer, I guess.
Okay, thanks.
Okay, if there are no more questions, well, let's thank speaker and
Thank you.
till next Monday. We're expecting Gayota to continue his lecture.
All right. Goodbye.
Thank you.
Thank you. Спасибо.